Hello, I'm William Michael. Today is April 9th, and it's 3 p.m. It's time for us to study classical geometry, and we're going to spend quite a long time studying Euclid's geometry. It's a very, very extensive book, and we're going to take our time and work through it. It's not a popular study these days because philosophy's been abandoned, but we're going to focus on classical geometry and study it for the sake of philosophy, which is why we're going to take our time and learn it well. I've already gone through the elements, which are the set of definitions, postulates, and axioms for the first book of Euclid's Elements. And in this lesson, we're going to get started with our first proposition. We're going to take some time to talk about propositions and how to study propositions, and then go through proposition 1, which is the first proposition of book 1. All right. Now, the question as we get into this study is, what is the real goal of the study of classical geometry? And geometry is not an end in itself. It's studied for the sake of higher pursuits as well. The study of astronomy assumes that you know Euclid's geometry. So one of the reasons we're studying geometry is so that we can go on to study astronomy, the fourth of the four classical mathematical arts. If you were to open up a copy of Ptolemy's Almagest, which I happen to have right here, Ptolemy's Almagest, this is the text for classical geometry. You'll see as you get into it that you're not going to be able to do anything unless you already know Euclid's geometry. And I'll just find you some samples. You can just see astronomy is just geometry applied to magnitudes in motion, bodies that are in motion, like the celestial bodies in the heavens. So one of the reasons we study classical geometry or Euclid's geometry is for the sake of the study of astronomy, because astronomy is just going to take what we've learned in geometry and apply it to objects, to bodies in motion. You saw me flash that book, just so you know if you're interested in it. It's Ptolemy's Almagest, translated into English by Professor Toomer up here at the top, you can see, published by Princeton University Press. All right, so this is the text that we use in our classical astronomy course. And, our goal in studying geometry is to prepare ourselves to be able to study astronomy as well, and then get into all kinds of interesting modern questions and dilemmas with respect to modern astronomy and physics and mathematics and so on. But if we want to understand classical geometry and classical astronomy, we've got to do the work, and that work is primarily mathematical work. So we're going to study the propositions here in Euclid's Elements, and in each book we'll be introduced to usually just some new definitions, and we'll continue to build one proposition at a time from this very first proposition based on the definitions and postulates and axioms of book 1, and we'll just continue to build into book 2, book 3, book 4, all the way through Euclid's Elements. God helping us, we'll get through the whole entire thing little by little, and then as time allows, move on into astronomy, which is a very rare study today, very challenging study today. But what's challenging about it is that it simply assumes and demands that we come with a knowledge and understanding of Euclid's geometry. So there's no point talking about astronomy if we're not going to work our way through geometry. Now, Euclid's geometry is really very simple. What we've got, and I share this on the study center, we've got a collection of truths that are established by Euclid concerning magnitudes at rest, which is the object of study in geometry. And if we look at the definitions, if we look at the postulates and the axioms and all of the propositions, We'll simply have a collection of truths that we then bring with us into other areas like astronomy and apply them to solve new problems. Now we could, if we wanted to, we could pursue geometry and astronomy the same way that we pursue the Christian faith. We could take the propositions, we could take all of Euclid's elements, which includes the propositions. We could just make a big list of all of the definitions, postulates, axioms, and propositions. And we can just take them and memorize them and refer to them by faith. We could just accept them as things that are either self-evident or conceded or already proven. We could do that. We could go into astronomy having simply studied to understand the content of the elements and being certain that they have been demonstrated in Euclid's propositions and his proofs. We could just take them for granted and go and speak of them and use them to solve problems in astronomy and study magnitude in motion. But obviously that would not be very satisfying to most people. It definitely wouldn't be very persuasive to anyone who we might enter into a discussion with who opposes classical astronomy. So what we're going to do is walk through Euclid's elements and study each proposition so we understand the demonstration for every single proposition that's made in the elements. But in the end, as I said, we're going to be left with a collection of definitions, postulates, axioms, and propositions, all of which have been proven, all of which are certain, and we're going to take them with us as our instruments, as it were, to study magnitudes in motion. Now, it's important to know, just as one last and brief introductory note, it's important to know that this geometry that we're studying here, classical geometry, is not the same thing as modern high school geometry. So if you're a high school student just looking for a high school geometry course, this is not that course. This course is really to be considered a philosophy course. It's for those who are interested in studying the 7 classical liberal arts. If you're looking for a high school geometry course, we have some other courses available. If you look on the Study Center, scroll down to the mathematics section down under modern studies towards the bottom of the course catalog, and you'll find modern math courses down there. You'll find plain and solid geometry for high school. And then we use the OpenStax series of books for algebra and trigonometry and things, and they've got high school geometry woven through them. So if you're looking for a modern high school course, this is not that course. This is a great addition to a high school curriculum, but really it's part of the classical philosophy curriculum, and it's to be studied by those who are interested in pursuing philosophy. All right, so having said that and provided that introductory information, I'd like us to jump in to Proposition 1. But before I do, one last bit. On the board behind me, you can see that I made a list of the 6 parts of a proposition. I did that just for reference. So if you're watching this video and we're going through this, we've got that in view. You can look up to that and remember the 6 parts. You'll notice that 3 of them are marked with asterisks because those are the 3 necessary parts of a preposition. Every preposition will have those 3 parts, and some prepositions have the other 3 parts, numbers 2, 3, and 4. The proposition, which is simply the statement of the proposition, that's always given first, and we're going to see that in italics in our textbook. We'll see the proposition, and then we'll see the exposition, which means the setting out of basically what's given to us in the proposition. Part 3 is the determination, and that means a clarification of what it is that we're seeking as we enter into the study of this proposition. So it's just good problem solving right there. We've got the problem set out, we've got the proposition stated. We then give the exposition to make it really clear what's been given to us, and then in the determination we make really clear what we're seeking. That's good procedure for problem solving. Part 4 is the construction. If a construction or diagram of some kind is needed or required by a proposition, it'll be included there in the 4th part. Then part 5 is the demonstration or proof, where we actually prove that the proposition is true. And then 6th, we simply summarize by pretty much restating the proposition. We summarize the whole study by declaring what was set out in the proposition and sought in the determination has in fact been done or proven. Okay, so those are the 6 parts of a proposition in the study of Euclid's elements. So with those in mind, let's go ahead and I'll share my screen and we'll take a look at the first proposition. So you can see here on the screen, we've got book 1, and we're looking at the propositions in book 1, and this is proposition number 1. So proposition 1-1. Okay, book 1, proposition 1. And then here in italics, you can see the proposition is stated, and that's the first part of the proposition, is the proposition itself. So we see on a given finite straight line, to construct an equilateral triangle. On a given finite straight line, to construct an equilateral triangle. And what that basically is telling us for the future is that if we are given a finite straight line, we can construct an equilateral triangle on that line, simply using the definitions, postulates, and axioms that are given to us in Euclid's elements. So given the elements and given a finite straight line, we can construct an equilateral triangle on that straight line, okay? Now you can see how that's useful, because if we move on into the future, if we're given a finite straight line and we're trying to figure out how we can solve a certain problem, we can say, well, we can construct an equilateral triangle on that finite straight line using proposition 1-1. So once we demonstrate and learn the demonstration that this is true, we can then use this proposition as another one of our tools in the solving of geometrical or astronomical problems. Okay. So what we want to see is if it's true, if it's really true that given a finite straight line, we can, using the elements, construct an equilateral triangle. Now, when you read a proposition like this, the first thing you should do is go back to the definitions and just look up in the definitions any terms that are included in the proposition that you saw in the definitions. Because every single detail is important. So for example, if we're told we have a finite straight line, you need to make sure you understand exactly what's meant by a finite straight line. And then we're told that we're going to construct an equilateral triangle. You've got to make sure you understand clearly what an equilateral triangle is. It's a triangle made up of lines that are equal. All 3 sides, trilateral or equilateral, all 3 sides are equal, okay? So on a given finite straight line, that is a line segment that is drawn between 2 points, construct an equilateral triangle. And Euclid tells us that we're able to do that with just the elements and the faculty of reason. Okay, that's our proposition. Next, the second part, you can see it begins with the word let. This is the second part of the proposition. This is the exposition. Let line AB be the given finite straight line. That's the exposition. Okay, what we've done here in the exposition is we've just clarified what is given to us in this proposition. Let AB be the given finite straight line. And if we look to this diagram, we can see at the center this finite straight line AB. That's given to us. The rest of this diagram is the construction that will follow, but this proposition begins with us given nothing on this diagram except for this finite straight line, line AB. That's what's given to us. And the question is, given that straight line, can you construct an equilateral triangle, a triangle with three equal sides? And we're going to seek to do that in this proposition, in the construction, and then prove that it is in fact an equilateral triangle and that it is in fact produced with nothing other than the elements as our resources. Okay, so we've got the first part here, the proposition written in italics, and then we've got the second part, the exposition here, beginning with let AB be the given finite straight line. Then we've got the third part of the proposition here, which is the determination. Okay. Thus, it is required, that is, what we're seeking, what we need to do here, is to construct an equilateral triangle on the straight line AB. Okay, so it makes it clear what we need to do. Notice also how from the proposition, we've moved from a general statement that applies to any finite straight line, and we've moved here in our study of the proposition to a specific finite straight line, this specific line, AB. That's the purpose of the exposition, and then the determination is to clearly articulate what it is that we're seeking. It is required to construct an equilateral triangle on the straight line AB. Okay, pretty simple. That's the purpose of the first three parts of the proposition, to get us to this point where we can very clearly understand what we're seeking to do in this proposition and what has been given to us to do that with. Now, in the next part, we begin the construction. One way you can usually identify the construction, sometimes it's difficult to identify and separate the parts of a proposition, but one way to identify the construction is that usually in the construction, we see references to the postulates. And you can see that here. Postulate 3 is used for that step. Postulate 3 is again used for that step. Down here, you can see postulate 1 is used for that step of the construction. So seeing the postulates noted is a good sign that you're in the construction part of the proposition. Okay? So here's how we go about doing this. Here's how we construct an equilateral triangle on a given finite straight line. Okay, step 1. With center A and distance AB. So we start with point A, which is the end of this given line. We start with point A. We use that as our center point. And we take point B as the end point of this line as the radius of a circle. And so using point A as the center and point B as the distance to the circumference, we read here, let the circle BCD be described. So with center point A at distance B, imagine planting your compass point there on point A and the lead of your compass out on point B, and then describing that circle. You can see that circle, BCD, around here. Okay, you see that circle? That circle in the diagram here, in the construction, that circle is constructed in this first step. With center A at distance B, describe the circle BCD. Okay, that's where that circle comes from. So that's step 1. So we've simply drawn a circle. So we have a finite straight line and we have a circle so far. The next step, we're going to do the same thing, starting with point B as the center and point A now as the distance to the circumference. We're going to describe the circle ACE around center point B. So we're going to describe the circle ACE, that's this second circle here. We're going to describe that about center point B. Okay, that's what's done here in this second step of the construction. So At this point, we've got a finite straight line drawn here, AB, which was given to us. We've got this first circle, BCD, which was constructed from point A at distance B using postulate 3 to justify doing that. We then constructed this second circle here from center point B at distance A, circle ACE. So we've got a finite straight line and two circles that have been drawn from the endpoints of that finite straight line. Now, in the next part of the construction, from point C. So point C is a point named where those two circles intersect. So that point at which the two circles intersect, we mark that as point C. From point C, in which the circles cut one another, the word intersect means to cut into. Point C in which the circles cut one another, to points A and B, let the straight lines CA and CB be joined. So we're going to draw straight lines from point C to point A and from point C to point B. And we're allowed to do that because of the first postulate, which says we're allowed to connect 2 points with a straight line. So we've now got 3 lines drawn because we just drew these 2 lines from point C to point A and from point C to point B. So we've completed this construction, which is the 4th part of our proposition. We've completed the construction. So having gone through that, going through these 3 steps, and you may need to reread them, and seeing how each step is justified by one of the elements, here postulate 3, here postulate 3 again, here postulate 1. We've created this construction, and you should be able at this point to look at this construction, look at this diagram, and understand what's going on there. It should be clear to you. If you look at that construction now and say, I have no idea how they got that, you need to go back and read through and follow the construction. But I think most students will have been able to follow along, and we'll see that now. How we were able to produce that triangle, because it's clearly a triangle, how we were able to produce that triangle on the given finite straight line AB. Okay, so we have produced a triangle. Now the question is whether we've actually fulfilled the requirement of the proposition, because the proposition didn't say draw a triangle on a given finite straight line. It told us we have to draw a specific kind of triangle. We've got to draw a triangle that is an equilateral triangle. It's a triangle with 3 equal sides. So now we've got to prove that we have in fact drawn an equilateral triangle. Okay, not only is it a triangle, but it's a special kind of triangle. It's an equilateral triangle. Okay. So now we move here from the construction, part 4, down to the demonstration, part 5, the 5th part of the proposition. And you can see that it begins with the conjunction since, or because. So we're into the proof now, okay? And you can pay attention to those conjunctions that suggest that we're giving reasons for things. Okay. So we've got to prove that we have constructed an equilateral triangle on that finite straight line AB. So here's how the proof goes. Since point A is the center of circle CBD or CDB, since point A is the center of this circle, then line AC, which is the distance from the center point to the circumference, must be equal to line AB, which is also the distance from the center point to the circumference. So line AC, remember we drew circle BCD starting from center point A at distance B, we drew this circle. So that point on the circle where point C is the distance from the circumference to the center point. That's the same distance as from A to B. So line AC is equal to line AB. And how do we know that? We know that from definition 15. That's the definition of a circle. So when we studied the definition of a circle, we learned that a circle is described as a figure where any point on the circumference is equal in distance to the center point. And because that's true, we learn that from the definition of a circle, then line AC must be equal to line AB. And that's the first part of our proof, okay? So we've proven that line AC is equal to line AB because they're the radiuses of one circle, okay, with a common point, point A. If we go to the second step of the demonstration, we really see the same thing from the other side. We see that the circle ACE was described around point B at distance A. And for the same reason, point C lies on the circle ACE. And point C is the same distance from point B that point A is. So line BC is equal in length to line BA because they're both radiuses of that circle. So again, line BC is equal to line BA, and that's proven by the definition of a circle, definition 115. All right, now we've shown that line BC is equal to line BA, and we've shown that line AC is also equal to line AB or BA. So what we've shown is that these two lines, line AC and line BC, are both equal to a common third line. And that's one of the axioms. You should remember that. You see down here it's noted common notion 1 or axiom 1.1. Okay, if two lines are equal to a common third line, line AB, then they are also equal to one another. So line CA and line CB, since they're both equal in length to line AB, they are proven equal to each other because of axiom number 1. So we now have proven that these three lines are all equal. They're all equal. That's this step here in the demonstration. Therefore, CA must also be equal to CB. Therefore, the three straight lines, CA, AB, and BC are all equal to one another. So not only have we drawn a triangle on the given finite straight line AB, but we've now proven that it is, in fact, an equilateral triangle. All of its sides are equal. Okay, that's the end of that demonstration. And then the last part of the proposition here is the conclusion. Therefore, the triangle ABC is equilateral, and it has been constructed on the given finite straight line AB being what was required to do. And this last phrase being what was required to do in Latin, that is quod erat faciendum, QEF, and that's a sign that this is a problem because something needed to be done. So if you're asked in the assessment, is this proposition a problem or a theory? It's very easy to tell. If it's a problem, you'll see what was required to do, QEF. And if it's a theorem, you'll see what was required to be demonstrated, QED, quod erat demonstrandum. All right? And that's it. That's the conclusion to proposition 1.1. So we see in this first proposition, we see all 6 parts of a proposition. We saw the proposition proper up here in italics. We saw the exposition here. We then saw the determination here. We saw the construction through here and the diagram that was produced by the construction. We then walked through the demonstration or proof of the proposition, and then we wrapped it all up with the statement of the conclusion. So all 6 parts of a proposition. All right, now the important thing to know as you walk away from this is The proposition here says that on a given finite straight line, we're able to construct an equilateral triangle. So if I were to ask you and say, is it true or false that given a finite straight line with nothing else but the elements, are you able to construct an equilateral triangle? And you should be able to say yes. And if I were to hand you a sheet of paper or give you a piece of chalk and ask you to go up to the board, you should be able to show me that it's true that you can construct an equilateral triangle on a given finite straight line. So that's the challenge of geometry, that you can not only claim the proposition to be true, but you can construct what's required by the proposition, demonstrate it to be true, and so not only know the proposition, but also be able to give the reason and proof for that proposition. So that's the goal of each proposition in classical geometry. And that's really all for the study of this first proposition. But notice what we've done here. We started out with a list of definitions, which were conceded. We could, and when I say concede, I mean we grant the definitions, not conceited, which means arrogant. Don't get those two words confused. Concede, C-E-D-E, concede means to grant something. We concede definitions. Definitions are called hypotheses in geometry. We concede or grant the definitions. We agree to use those names with those definitions. We then looked at the postulates and saw what we're allowed to do, what steps we're allowed to take that don't require any great mental leaps, but are pretty simple and understandable. We saw them in the postulates. And then we saw the common notions or axioms. And that was all we had to work with. We just had those definitions, postulates, and axioms, the elements. That's all we had. And we used them to do something else, to discover some new geometrical truth. We used them with the help of reason to invent something new, namely this first proposition. And now that we've established this proposition and demonstrated its truth, it can be added to the number of things we now have to work with. So now we have definitions, postulates, axioms, and one proposition. So we've added to our toolbox. We've added this, that if we're given a finite straight line, we can construct an equilateral triangle on that finite straight line. We can show how it's done. We can prove that it is in fact an equilateral triangle and use that to move forward in the investigation of geometry with absolute certainty, knowing that every single step of what we've done has been demonstrated to be true. All right, so that's all for proposition one. You're going to need to study these on your own. You're going to need to memorize the definitions, to memorize the postulates, to memorize the axioms, to memorize the proposition, that is the proposition proper, actually stated in italics, and then be able to provide the construction, if possible, if required, and give the demonstration, which is definitely required, and the conclusion. So what you need to be able to do is to take the proposition and show that it's true by actually doing it and then explaining the proof for it, so that not only can you use the proposition, but you can prove that anything you solve with that proposition is in fact true according to the elements of geometry. Okay, so that's the challenge. So eventually in the classical geometry course, you're going to be challenged with examinations where you're required to prove a proposition, and it could be any proposition, and there are going to be many of them. But you've got to know how to show the truth of a proposition, because it's one of our tools in our geometry toolbox. And as you'll see, when we get to astronomy, you've got to have a full toolbox in order to do the work of astronomy. And this is us moving like apprentices and one by one adding a new tool to our toolbox every day as we work. Okay, so that's all for proposition one. Go back, review the definitions, postulates, and axioms, memorize this proposition, be able to prove that this proposition is in fact doable and true. And in our next lesson, we'll move on to study the second proposition. I hope that's helpful. If you have any questions at all, any questions about anything in this lesson or in geometry, there's a support forum on the geometry course page in the study center of the Academy. You can post any questions you have on the study center at any time. I usually see them within minutes of the time that they're posted, and I'll reply as soon as I get a chance. Any questions, post them on the forum or send me an email. You can write to mail@classicalliberalarts.com. As a student, you have to remember it's your responsibility to seek understanding. You have to ask, seek, and knock. You have to study and study and study. And when there's anything you can't comprehend, you've got to ask for help. That's part of being a student. Okay, so study this proposition on your own. Make sure everything is crystal clear. Make sure that you can construct and prove this proposition, and we'll move on next time to the next one. All right, I hope that's helpful. God bless.